Um, this video, I am going to do a few problems from Chapter 7, which was uploaded as a Chapter 7 Exam 2 review. So I'm going to work on some of the problems from that review. The first question was asking about naming some alkenes and cycloalkanes. So the first question is asking, write the line structure for each of the following vinyl cyclohexane. So we draw the cyclohexane first. So here we have the cyclohexane, and then the vinyl is this structure. Okay, so that's vinyl cyclohexane. The next question is about 4E2,4-dimethyl-4-hexene. So first of all, you draw the 2,4-dimethyl-4-hexene. So 1, 2, 3, 4, 5, 6, and then at the second position and at the fourth position we have dimethyl, and at the fourth position we have a double bond, and then it's telling us it should be E. The designation should be E. So if you recall, the E and the Z designations, the higher priorities should be on the opposite sides and the lower priorities should be again on the opposite side. So if you look at this double bond, here we have the low priority, and here we have the high priority, and here we have the high priority, and here there is hydrogen, right? There is hydrogen here, which is the low priority, right? So we have high priorities at the opposite ends. So this depicts the E structure. Okay, let me give you another example. So E and Z means, so when you have a double bond and you have substituents at the double bond, say for example I have a Cl here, a hydrogen here, and then say I have a CH2, CH3 and a CH3. Okay, so the way we denote E and Z designation is you look at the two halves of the two sides of the double bond. Again, priorities are given with respect to the highest atomic number, like we did in Chapter 5. So the higher priority between these two is chlorine, because it's the higher atomic number. So this is my high priority, this is my low priority. Here we have carbon connected to another carbon, so this becomes my high priority, and this is just a carbon, so this becomes my low priority. So here if you look, the low priorities are on the same side, high priorities on the same side, so this will be an example of a Z isomer. Okay, another example just to make sure that you understand. So again, if you have a double bond and then say I have a carboxylic group here, and then say I have a CHO group here, and then here I have a CH2, CH3, and then I have a Cl here. Okay, all right, so now if you look, how do I designate E or Z for this compound? Again, divide it into two halves. Between these two, which one would be the high priority? Carbon. Here again another carbon connected to another carbon, but this connected to chlorine, so this becomes my high priority. This is my low priority. Here we have a carbon connected to the two oxygens, so this is my high priority. Here is connected to only one oxygen, so this is my low priority. So here we have high priorities on the opposite sides, low priorities on the opposite sides, so this should be a E isomer. Okay, so that's how you designate E and Z to before the names of the alkenes, to show whether the isomer is a Z or a E. The second question, it's asking you to name this compound. Now if you look at this one, so you have to figure out the longest chain first. So let's look at, so we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like it is a decane, right? A decane, but there are double bonds in it. So you have to make sure that you are numbering it correctly. So this is a 1, 2, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So the second position and the 8th position, you have methyl groups, right? And then 1, 2, 3, 4, 5. At the 5th position, you have an ethyl group, right? And then also we have the at the third position you have a alkene, and at the 8th position again you have an alkene, right? So you will name this as or should we number from this side? So let's look at the numbering from the other side. Let's put a red color to it. Okay, let's look at this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if you look at here, we have at the 2nd and 7th. If you look at from this side, you have 3rd and 8th. So we will go with the red numbering. Okay, so now we will name this as 2. Now look, this is again priority wise. This is a high priority, this is high priority, low priority. This is high priority, low priority, right? So they are in the opposite side. So it should be a 2 at the 2nd position. You have the 2E, comma, at the 7th position, we have another double bond, which is, let's see if it is E or Z. Look at this one is high priority in the opposite side, so it is again an E, so 7E. Okay, so at the 2nd position and at the 7th position we have the double bonds, and you have to designate them as 2E7E. And then you have at the 6th position you have a ethyl. You have ethyl, and then followed by at the 3rd and the 9th position, right? At the 3rd and the 9th position you have dimethyl, deca, because it's a 10, deca 2,7 diene. Okay, this is how we name this compound. It's a little complicated, but if you analyze it, this is how you name it. Now this one is much more simpler, so you can start numbering this from the side. 1, 2, 3, 4, 5. So you have 1 ethyl, 3 methyl, cyclopentane. Okay, let's go to the next one. Next question. Predict the major product. Okay, so we have a alkene. Let me erase this one. Okay, we have an alkene and we are reacting it with HBr. And what should be the product? Okay, so the product should be where the so this is where we follow what is called as the Markovnikov's rule. We talked about this in the class on last week. So Markovnikov's rule, which tells us that the Br will go to the more substituted carbon and hydrogen will go to the less substituted carbon. So we are looking at addition reaction. Okay, so this carbon will get the hydrogen and Br will go to this carbon atom. Okay, so we still have the 2 carbons here. See, these are the 2 carbons. This carbon atom gets the hydrogen, this hydrogen here, and this carbon atom gets the Br, right? Okay, now let's look at the mechanism of this reaction. So it starts with the double bond attacking the HBr, or the hydrogen of the HBr molecule. So this is a nucleophilic electrophilic attack. Br pulls off the electrons towards itself, making this the electrophilic end. So the double bond is rich in electrons. It acts as a nucleophile, takes the proton, and the first step is the formation of the carbocation. Okay, and this hydrogen here is attached to this carbon atom. In the next step, what happens is Br minus, which was kicked off here in the first step. Okay, look, Br takes off the electron, so it gets a charge here. It will go ahead and, or maybe we can do it in the next step. All right, let's show it as a next step. That in the Br, now I'm not going to draw the hydrogen, okay, because it's understood that the hydrogen is there. The Br minus now acts as the nucleophile and attacks at this carbon atom to give the product, which is your addition product. Okay, So that's what I have drawn here. I have not drawn the hydrogen because it's understood that we have the hydrogen in that carbon atom. All right. So simple mechanism. This is an electrophilic addition reaction. Electrophilic addition reaction of HBr on alkenes. Okay. All right. Next, it's asking you to draw an energy diagram for this same reaction. Label starting material, products, intermediates, transition state, and energy of activation. Also indicate the rate determining step. Okay. So for drawing the energy diagram, you need to label the two axes. This is your energy, and this is the progress of the reaction. You're plotting energy versus progress of reaction. Now, if you look at the previous mechanism, this is a two-step mechanism, right? Two-step. So you will have two bumps on your graph, which can be drawn like this. Okay. Now, the first one, this is your transition state 1, and this is your transition state 2. Okay. Here is where your carbocation intermediate is formed. So I equals to the carbocation intermediate, which would be your reactants. Here is your reactants. So we have to label the reactants, and here is your products. Okay. And then the total energy change between the reactants and the products is represented as delta G, and that is the change in free energy. The energy of activation, you again have two energies of activation. From here to here is EA, say we call it as EA1, and then from here to here, this small energy of activation is EA2. Now when you look at this, has got higher energy of activation, so your first step should be your rate determining step. Okay, so remember that in the slowest step, right, when you have multiple steps, the slowest step determines the rate of the reaction. So the first step is the rate determining step. So that means this step, okay, this is your rate determining step, because that's the slowest step, formation of carbocation. Okay, once the carbocation is formed, this Br minus will quickly attack and forms the product in a fast reaction, and you can see that the energy diagram, the EA2 is pretty small, so it can easily do this reaction. Okay. All right, next question. Circle all carbocations that can undergo rearrangement to form a more stable carbocation. Now for this, you have to remember that the tertiary carbocation is more stable than a secondary carbocation, is more stable than a primary carbocation. Now when you look at this one, is actually a primary carbocation. Okay, but can it rearrange itself? And whenever carbocations have the possibility of rearrangement by hydride shift, they can do that. But in this case, it can move from here to here, to a primary to a secondary carbocation, by moving the hydrogen from here, okay, for a hydride shift. So this one can, yes, indeed go, it can do a rearrangement. What about this one? This is already a tertiary carbocation. It will not have any motivation to rearrange, so not this one. What about this one? Yes, this is a secondary carbocation, but if you move this hydrogen from here to here, it can actually get the carbocation at this position. Okay, so let's redraw this, rearrange. So this can rearrange to where the hydrogen here, okay, this hydrogen can actually shift to here, this position, and leaving room for this carbocation to move to this position, to become going from a secondary to a tertiary. Okay, so this will be a case where you can do rearrangement. Now here, this is a secondary carbocation. If it moves, it won't move this side because this is primary. Even if it moves here, that's another secondary, right? So there is no rearrangement possible. So the only two carbocations that can undergo rearrangement are this one and this one. Okay, so this process where hydrogen or hydride shifts to give room to a more stable carbocation, that's called as a hydride shift. hydride shift. Okay, and this happens very often in carbocation mechanisms, where if there is a possibility of a more stable carbocation to be formed, then hydride shift can happen. Okay. Next question. In the reaction below, label the nucleophile and the electrophile. Draw arrows on the structures showing electron flow. So if you look at the product, the chlorine has attached itself to this carbon atom. So this becomes my nucleophile, the electron rich. This is my electrophilic center. We draw an arrow from here to here to give you the product. Okay, so that's how you show the mechanism. Here, arrange the following bicyclic alkenes in order of increasing stability, least stable to most stable. Now remember that in alkenes, the more substituted alkenes are more stable. Okay, so if you look at this double bond, it has got 4 substitutions. We have 1, 2, 3, 4. So this is a tetra substituted alkene. Now if you look at this alkene, there is a substituent here, this is substituent here, right? And then the other 2 are hydrogen. So this is a di-substituted alkene, di-substituted. And then this one is actually a tri-substituted. See, there is this substituent, this one, and this one. So that's a tri-substituted. So the greater the substitution, more stable is the alkene. So in this case, 1 would be more stable than 3, which would be more stable than 2. Okay, because greater the substitution, more stable the alkene is. Okay. Now, predict the structure of the alkene you would use to prepare the alkyl halide below. This is the alkyl halide, so we can draw the structure like this. Okay, if you add a HBr to it, you will get the product that's given here, like this. Okay, or you can have this one too, which is the same as this one, right? You think that this is different. No, it's the same as this one, so we don't need to draw this. Okay, so we have this is the product. Predict the major products for the following reactions. So here again, if you look, let's draw the skeletal structure of this. Okay, so 1, 2, 3, 4. 1, 2, 3, 4, and at the second position you have a methyl group, and the double bond is here. Okay, so this is the compound, and we are treating it with HBr. So if you look at, let's just randomly draw the mechanism here. We have a double bond which is acting as a nucleophile, attacking the hydrogen, which is your electrophilic center, and you get the carbocation intermediate, right? And the hydrogen goes to this carbon atom, right? Now if you look at, remember we talked about carbocation rearrangement. So here, since the carbocation, if it moves here, it gives a more stable tertiary carbocation. So a hydride shift will happen. A hydride shift will happen where the hydrogen here, the hydrogen shifts to this position. Okay, shifts to this position here and giving room to the more stable tertiary carbocation. Now the Br minus, which was kicked out in the first step, it will go and attack the carbon atom here and give you the product where the Br is attached over here. Okay, so that should be my answer to this question, that the Br is attached to the more stable carbocation, which is the tertiary carbocation. Got it? So this should be your answer. Next question, determine the degree of unsaturation in the molecules given below. Okay, and draw one plausible structure corresponding to the formula. Now, if you study from chapter 7 how to calculate the degree of unsaturation, if you have nitrogens in the molecule, you have to subtract one hydrogen from your given formula. Okay, so we have C5H9N. If you have a nitrogen in the molecule, you have to subtract one hydrogen, so we get C5H8, and then what you do is you compare it to the saturated analog, that means if you have 5 carbon atoms, then ideally you should have 12 hydrogen atoms, right, to fulfill its valency. So you subtract the 12 with the given number of hydrogens, 8, that's 4, and you divide it by 2, you get degree of unsaturation as 2 for the first one. Okay, and then that means when you have 2 degrees of unsaturation, you can either have a ring or a double bond. Okay, this double bond corresponds to 1 degree of unsaturation. A ring corresponds to another degree of unsaturation. Okay, so maybe you can draw something like this, where you have 5 carbon atoms, and say, so we have 1, 2, and then maybe put a double bond in here and an NH2. So let's count the hydrogens and see, we have 1 hydrogen here, 1 hydrogen, we have 2 hydrogens here, 2 here, and then 1 here, right? So that means 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 hydrogen atoms, 1 nitrogen atoms, and 5 carbon atoms. So this could be a plausible structure for the formula that's given. Let's look at the next one, C6H6Cl3Br. Okay, so whenever we have halogens, you add that many number of hydrogens to the formula. So we have C6H6, but then 7, 8, 9, and 10. So this corresponds to C6H10, and then you compare it to the saturated analog, which is C6H14, right? That should be the saturated analog. Subtract 14 minus 10, that equals to 4 divided by 2. So you get this one also a degree of unsaturation of 2. Okay, so you can again draw a plausible structure. You can have 2 double bonds and then 6 carbon atoms, 1, 2, 3, 4, 5, 6. Maybe you can have a double bond here, a double bond here. You can have a chlorine here, okay, a Br, maybe another two chlorines here, right? You can draw all these structures which are possible, but you should have 2 degrees of unsaturation. So we have 2 double bonds which correspond to 2 degrees of unsaturation. Let's just make sure we have the right number of hydrogen atoms. We have 1, 2, 3, and then 4, and 5, and 6. Okay, so this could be one of the structures possible with this formula. Okay, so remember that degree, if you have a ring or a double bond, it corresponds to 1 degree of unsaturation. Okay, ring or a double bond. If you have 2 double bonds, then it corresponds to 2 degrees of unsaturation. If you have 2 rings, that also corresponds to 2 degree of unsaturation. A triple bond corresponds to 2 degrees of unsaturation. Okay, just 1 double bond corresponds to 1 degree of unsaturation. So that's how you have to find out how many degrees of unsaturation are there. So for example, if I give you this structure, okay, like a benzene, and ask you how many degrees of unsaturation are there. So 1 ring, then 3 double bonds, right? So we have 3 plus 1, 4. So degree of unsaturation in benzene is 4, because each double bond corresponds to 1 degree of unsaturation, and the ring corresponds to 1 more. So 1, 2, 3, and 4 degrees of unsaturation. Okay, all right. That's it. That's the number of questions I had for reviewing chapter 7. I had put up a separate review for chapter 4, 5, and 6. So you should be able to look up in those. But this chapter 7, I wanted to cover it because we didn't have time to cover it in the class. Right? Okay. Good luck with your exam.